All right, guys. Thanks for watching this video. Today we're going to talk about problem 7.39. What is the moment of inertia of an object? Okay. We need to talk about what a moment of inertia is. Okay. I posted two videos on Canvas that kind of give examples of what the moment of inertia is. Now, just in general, we can think of the moment of inertia is it's kind of like mass, right? So it's basically the resistance of an object to spinning. Okay, every object has um, basically some resistance to spinning. Okay, and it depends on the shape of the object. Okay, and things have different axes of rotation. Okay, for example, let's take this bottle here. Now I could spin the bottle like this. Okay, so if I spin it like this, or if I do it sideways, right? So the bottle can either spin this way. Okay, or it could spin over like this. Now, um, one way is harder to spin it than the other. If I go like this, or see, it's pretty complicated. Okay, so I'm gonna go like, oh, okay, so if I spin it that way, it's pretty easy to get it spinning around this axis, right? And now, if you ever want to find the center of mass of something, that's basically where the center of mass is kind of focused around. And it doesn't necessarily have to be inside of the object necessarily, okay? But generally speaking, the best way to find the center of the mass is if you try and balance the object, okay? Because if you get something balanced, right? My finger has to be right below the center of mass of this object. So the center of the mass is right about here, okay? That is the center point where basically gravity acts on that thing, okay? Now, if I put it like my finger like this, okay, and the center of mass is right here, then gravity is going to create a torque. Okay, so gravity is going to be acting at a distance, and there's going to be some torque there. Okay. Um, Now, generally, there are tables which list all the moments of inertia. Okay, and let's actually watch some videos together. Okay, and then we're gonna do some problems. Okay, so let's go to the module here. We'll watch this first video together.
This incline. And the one with the greater rotational inertia will lose the race because it will have a greater resistance to a change in its state of rotational motion. Now, right now, the state of rotational motion of both objects is zero. They're not rotating. Once I remove the piece of wood, one of them is going to rotate more quickly. Let's see which one that is.
All right. Slow motion. Sweet. That guy is pretty sick. Man, that's a nice setup though. I was like, wow. He uh he doesn't have a lot of enthusiasm, but he has some cool demos, man. I wish I had that. All right, but those two objects are different because one is a solid disk and the other is a hollow cylinder. Okay. Now those things have different moments of inertia. That means um, there's a different tendency for those to want to be able to spin. And in general, we can look up the moment of inertia of different objects. Okay, so let's look at the moment of inertia. Okay, so let's watch the video again. It's
The
pretty
greater
awesome.
rotational inertia will lose the race because it will have a greater resistance to a change in its state of rotational motion. Now, right now, the state of rotational motion of both objects is zero. They're not rotating. Once I remove the piece of wood, one of them is going to rotate more quickly. Let's see which one that is.
Whoa, it was definitely the solid cylinder. Man, that thing was going fast. All right, let's look at the equations of the moment of inertia of different objects. Then we're going to talk about a little bit about torque. Yeah. And we're going to get to the, where did that go? Oh, did I pass it? I think I passed it. Oh, wait, I passed it again. Oh, slow down, man. Slow down. Okay. So we had basically two moments of inertia. Okay. And this table in the slide is invaluable. Okay. So what you're going to do is you're going to look over here on this table and you're going to look up I. That's what we call moment of inertia. M was already taken by mass, and so yeah, I makes sense, right? Moment of inertia, that makes sense. It's an I, okay. But for whatever your object is, you're gonna go to this table and you're gonna look it up, okay? Now, all right. So hollow discs have a higher moment of inertia. Okay. So this hollow disk, see, all of the mass is out here on the edges. Okay. And so that means that you can almost think about it's going to take more energy to basically get it going. Okay. Let's look at an example of why. Well, we haven't really talked about kinetic energy yet. Okay. And so um, it's a little bit problematic if we were going to talk about kinetic energy at this point. But basically, the thing with a higher moment of inertia, right? It takes more energy to get it spinning, right? So gravity is the thing that's going to cause us to start spinning as it goes down a ramp. And if the mass is distributed on the outer part of the object, it's going to take more. Um, more energy to get it going. Okay, so for the problem here, it says the moment of inertia of a spherical shell about the diameter is 2/3 mr squared. Okay, um, and this is important for a lot of reasons, because it tells us a lot how things can rotate. Okay, how they rotate. Are they going to rotate fast or are they going to rotate slow? Okay, now. Angular acceleration, okay, moment of inertia is related to torque, okay? That means that as you apply a certain amount of torque, okay, the higher your moment of inertia is going to be, the lower your angular acceleration is going to be, okay? And that's an important concept, okay? And it's related to Newton's second law. So some people call this Newton's second law of rotation. Okay, so this is angular acceleration caused by torque. All right, so we've got this expression here. Let's take this equation and we're going to do an example. And then we are going to, oh, I need to plug in my camera. Alrighty, there's my beautiful pine tree. Okay, so let's talk about torque. So I'm going to write down this equation here. There's going to be alpha, that's our angular acceleration, times T net. Okay, that's our net torque times I. Okay. All right, now let's talk about the moment of inertia of those two objects that we looked at. Okay. Well, for a solid or a hollow cylinder, right? Here's a cylinder over here, and this thing is, let's say it's hollow, okay? It's going to look something like this, okay? And it's hollow. This is going to be mr squared, okay? And r is my radius here, okay? The radius on the outside. Now, if we have an object, okay, if it's a solid sphere, let me just make sure I'm writing this down right. Yep, I got that right. So a solid sphere here. Okay, this is a solid cylinder. Okay, this is going to be 1/2 mr squared. Okay, so these two different objects, and let's write down a hollow sphere while we're at it. Okay, we got this is solid. We'll put solid cylinder, and this is a hollow cylinder. Okay, and then we've got a for a hollow sphere, it's going to be 2/3 mr squared. Okay, and this is so here's my sphere, and then this is just like a shell, basically. It's like a pickleball, kind of. Okay, or maybe even a tennis ball. Most sports balls are hollow spheres. See? That's because there's no fun without physics. Let me write down the most important equation of the semester. If you don't remember anything else, okay, I want you to remember this one equation right here, okay? Physics equals fun. Boom! This is the most important one right here. Remember, because there's no sports without physics, okay? No games, no sports, no fun. Because physics is fun. Physics equals fun. Wonderful. Okay, so let's plug it in here. Okay. Now, we need to talk about let's talk about torque due to gravity. Okay, so if I put one of these guys on a ramp here, okay, let's put it like here. Let's say this is a hollow sphere. Okay. Now, what's interesting about a hollow sphere, okay? Even though this thing is hollow, the center of mass is not actually located in anything made out of mass, okay? It's actually in the middle of this empty space. Okay? So, yes, that's true. And so gravity is acting on this thing here basically it's pretty much like right there, like all the mass is centered right there, okay? But it's not. Okay, so we're gonna have our radius here. Okay, there's our radius. Okay, so that's R. And before we talked about torque is equal to what did we say? It was R times F. So it's gonna be R times the weight or M times G. Okay, and these two things are crossing. Okay, so right here. Okay, mg is going down that way. Okay. And we got a sine of phi here. Okay, now am I making this too complicated? Hope not. Okay. Well, anyways, let's check it out. Okay. So basically, right here is our angle phi. Okay. That's our angle phi. So R is going this way, and then phi is this angle right here. I'm gonna make that purple. Boom. You know what? I'm gonna stop sharing this right now so we can focus on the picture. All right, so the angle here, that's phi. Okay, that's my angle phi. Okay, so when I write down my equation for torque, tickety torque. I don't know why I said that. That was really cringe. My expression for torque, all right? How did I get that? Well, I said, okay, torque is equal to R cross F. Okay, well, what's F? F is going to be m times g because that's my weight. That's the weight of this sphere, right? The weight of the universe sometimes is heavy, okay? F is my force. R is the radius of my sphere. I'm going to put that, I'm gonna put my radius in red here. R, that's R right there, okay? Boom, R, okay? So we've got R here, okay? Cross the F or weight, right? In this case, F is equivalent to the weight. That's the only force acting on this, right? It's the weight. It's pulling it down. So we've got an angle here. Now, does our equation make sense? Okay. I always like to think about, all right, does this equation make sense? All right. Well, first of all, if we know that sine equals zero, okay? Sine of zero equals zero. So 0 degrees here, okay? That means if at 0 degrees, my it's basically flat. Well, it is flat, okay? And so at 0 degrees, the torque on this thing is going to be zero, okay? It's going to be zero. All right, so let's plug this in here. Now, how did I get this equation? I said R cross F. F is my weight here, and then sine of phi. That's because I have the cross product of two vectors. Okay, how does the cross product work? Okay, basically, here let's do this. Okay, we're doing some vector algebra. Okay, basically, okay, we got R here. Okay, R is going that way. That's the radius of our hollow sphere. Ooh, hollow sphere. You know, that sounds like a Jujutsu Kaisen power, right? Sukuna uses hollow sphere. Yugi Ichidori's moment of inertia is not powerful enough to deal with Sukuna's hollow sphere. My son watches a lot of Jujutsu Kaisen. If you don't know what I'm talking about, don't worry. That was from anime Jujutsu Kaisen. Very popular amongst younger people, or so I hear. But anyways, so hollow sphere. I'm gonna tell that to my son. He's gonna be like, Dad, you're so lame. That's so cringe. Okay. Then F down here, this is my weight. Okay, so I'm gonna say F is weight. Those are vectors. Okay. Now when you cross two vectors, okay, basically you take your hand, point it in the direction. Oh, okay, you gotta use the right hand rule here. Okay, so do this with me. Point your hand in the direction of R and then curl it around a W. See? And then look, my thumb is pointing into the page. That's which way the torque is going. I go from R to W and look at my thumb. See, if it was W to R, my thumb would be going that way, but it's not. See, put your fingers in the direction of the first vector. R. See? R cross F, R cross F. F is W. I go R to F. Right hand rule. Boom! Thumb into the page. Okay, well, anyways, when you do that, you get a third vector that comes out of the page, right? It's like in 3D. Can we draw this in 3D? Can we draw a 3D arrow? Yes, I think we can. Look at this arrow. It's coming out of the page. See, our arrow, it's 3D. So you can draw in 3D. Look at that. Look at that arrow coming right out of the page. It's like jumping out at me. Ow! Don't poke me in the face. Ow. Jeez, torque vector. Ow, it hit me right in the nose. Oh my gosh. See, it's an arrow coming out of the page. I mean, honestly, if you had 3D glasses, it would be better, but you didn't bring me any 3D glasses. Okay. Here's my angle phi. Okay, so this is my 3D picture. Okay, this one's coming out of the page, it's right at your face. Okay, just imagine that. All right, so I'm gonna plug this into my equation here for alpha. Okay, I'm gonna put it in here. So we got R times M times G times sine of the angle phi. Okay, and then my moment of inertia for a hollow sphere is M over R squared. Look at that. And guess what? What's really crazy here? Okay, look at that. The M's cancel. Sukuna cancels the mass. Ugh. Oh no. Yuji's in trouble. Wait, Yuji wouldn't battle Sukuna because Sukuna lives inside. Okay. That that was clearly wrong. This R goes away, so we get an R here. So look at this. Alpha, okay, our acceleration is going to equal G times sine of phi divided by the radius of our sphere R. Okay. That's for this one. And instead of I here, if I put in a 1/2 here, okay, So this is my angular acceleration. This is angular acceleration. Basically, how fast is it going to accelerate? How fast is it going to start spinning? Okay. That one was for my that was for my hollow sphere. Let's do a solid sphere now. Yeah, let's do a solid sphere. Okay. Let's totally do a solid sphere. All right. Here's my solid sphere. I'm gonna have alpha. I'm gonna do the same thing right up here. I'm gonna plug all this stuff in here. Okay. This is fun. R times M times G times sine of my angle phi. And now we're going to put in the moment of inertia I here on the bottom, right? We're going to put in there. But now we have a 1/2 mr squared, okay? And this is r here also. But look what happens in this case. If 2 is in the denominator of the denominator goes to the top, I'll show you. See, I'm going to multiply here the top and the bottom by 2, okay? This 2 cancels. This 2 cancels. I get a 2 in the numerator. Okay. This R cancels right here. My masses cancel. Okay. And look at this, guys. Oh, man, this is amazing. Now we have G times sine of phi times, and that's divided by R times 2. Look at that. We get a factor of 2. Okay. So look at this. The acceleration for this one, okay, it's 2 times higher than for the hollow sphere. The solid sphere wins. Okay. That's just based off of this acceleration. Okay. Wow. That is pretty cool. See, we actually proved something useful here today. Okay. And we watched that video showing that the solid sphere actually goes faster. Okay. See, this is one thing that I actually really like about physics. Okay. Because it doesn't matter if you believe in the solid sphere or not, it just goes faster. It is independent of what your opinion is or you believe because you can test this. This is repeatable. And this is how we know that things are real in science, okay? Because no one can tell me any differently about the moment of inertia, right? Because I know what it is, right? I can prove it. Now, maybe not everything that you can prove, but many things you can prove. And so if people try and argue with you about science, you need to understand that they might not know what it means to prove something is real, but you do. So you are part of the enlightened few now that know about science. And so that is a big responsibility. All right, let's look at this problem here because the problem says, okay, what does the problem say? Here's our problem. Another problem. But we will find a solution. All right. A table tennis ball has a mass of 2.7 grams and is 40 millimeters in diameter. Okay. What is its moment of inertia about an axis that passes through its center? Okay. And what we found here, okay, this is the big takeaway from all of this. Okay. That if something has um a smaller moment of inertia, if the moment of inertia is slower, it's going to be easier to make it rotate, okay? It will rotate faster because it will accelerate faster down a hill, okay? So question time, if you're thinking about a muscle car, okay? They're like, I'm gonna buy a new car and I want to get the fastest possible car. What kind of rims should you get for your car? Does it matter? Yeah, it freaking matters, man. The moment of inertia is a big deal, okay? You don't want that Tesla beating your $400,000 Lamborghini, or actually $450,000, right? You want the Lamborghini Aventador, obviously, and you're definitely gonna get the $30,000 insane package upgrade so you can be faster than an electric car. Of course, I mean, It does take your gas mileage from 5 miles per gallon to two, but at least you're faster than a Tesla. And that's really the only thing that matters. You know what I'm saying. Anyways, let's do this problem. I forgot why I was talking about this. Okay. Back to the problem. Yes. Let's read the problem. I'm gonna share my screen here. A table tennis ball has a mass of 2.7 grams and it's 40 millimeters in diameter. Okay, and we know that that is a solid sphere. Look at this. I wrote down the moment of inertia. This is my ping pong ball. I prefer to call it a ping pong ball. You can call it table tennis. I don't know. All right, what is the moment of inertia about an axis that passes through its center? Okay, so here is this axis. It goes right through the center of my ping pong ball. All right, I got the formula right there. I am going to put this in kilograms and meters. Yeah, because if you don't, that's going to get it. We're going to get it wrong. Okay. So it's going to be 2/3, okay, times grams to kilograms. That's going to be there's 1,000 grams in a kilogram. So I'm going to move the decimal place over three. It's going to be 0.0027 kilograms. Oh, I'm running out of room here. Okay, we're gonna switch colors. There we go. All right. So I'm just plugging the numbers in here that it gave me. 40 millimeters in diameter. Okay, that 40 millimeters, I need to convert that into meters. Okay. That's the same as saying 4 centimeters. And that is gonna be, okay, we're gonna have to multiply in here. That is gonna be 0.04 meters squared. Okay. And did I do that right? Yeah, I think it's right. Okay. I had to put the surface of my sphere interrupted the parentheses, but you can imagine you can multiply through the table tennis, right? That was a small physics joke. You can multiply through it. All right, let's throw it into MATLAB. Boom. Throw it into MATLAB. Oh, that was. People tell me that I shouldn't sing, but you see, I understand harmony on a theoretical level. Unfortunately, I just can't like make my body do it, but I understand it theoretically, just like dancing. Like I understand sinusoidal motion on a theoretical level, but just can't dance. You can't, you just don't get everything in life. 0.04 squared. Oh, we want it squared. All right, the moment of inertia is what? An error. Oh, we didn't put in the multiplication sign. I thought it was implied, but no, it apparently wasn't. I don't like all the zeros, so I'm gonna do format short. That's too many zeros, man. Okay, we got a moment of inertia here. Let's check it out. I is gonna equal 2.88 times 10 to the minus 6. And what units do we have? We have, oh, that's what? 10 to the minus 6 times our units. We got kilograms and meters squared. Kilograms times meter squared. All right, let's put it in. Let's put it in, man. I don't know. Okay, how do we do scientific notation? Oh, shoot, I shouldn't sing. Well, let's try E. I don't know if it's gonna like E. It probably won't like E, but you know what? I think you should be able to do this. -6. You can do this on MATLAB. All right, kilograms times meter squared. Yeah. Is it gonna like the E? I probably not, but the value should be entered as a single number or in scientific notation. Fine, we'll do it. 10 to the -6. There it is. Does it like my answer? What? Oh, guys. Look what I have done. Oh, I didn't read. Do you know what I did? All right, can you spot the mistake? Oh, the pain, agony. Where did we go wrong? I violated my own rule. I didn't read the problem because if I read the problem, I would have known that it said diameter, not the radius. It clearly says diameter. And also, I think it was because my sphere messed me up. I'm not gonna lie. Did I put that in MATLAB? I did put the 2/3 in MATLAB. Okay. Okay. We're gonna try again, ladies and gentlemen. Okay, so we're gonna put in the radius. So we'll have I is gonna equal, we got a sphere, 2/3. Don't forget that. Okay. The mass of the sphere, I think we did that right. That was 0.0027 kilograms. I feel confident about that. This part is definitely that is wrong. That we should have the radius, not the diameter. Well, half of this is going to be 0.02 meters squared. Okay. That I see I didn't read the problem. It clearly says diameter, not radius. Okay, well. All right, let's throw this into MATLAB. So, if you ever get a problem wrong, please don't feel bad. It is totally fine. Okay, so that's different. Okay, we got that is different. It's painful that we had to use an attempt, but nonetheless we got there eventually. 7.2 times 10 to the minus 7, and we had kilograms and meters squared. All right, let's try it again. No, I do not want the wait, previous answer. Yeah, no, I want to put in a new answer. I want to put in a new answer. 7.2 times 10 to the minus 7. Yes! We've done it. Success! We did the moment of inertia and we got it. And hopefully you understand a little bit about the moment of inertia, okay? The main thing is that objects with a higher moment of inertia have more resistance to rotating. Okay. So the higher the moment of inertia is, the more force you're going to need to rotate that object. That's what this is really about. And so we can compare it to mass in a sense, right? If you have a higher mass, it takes more force to get it moving. Thanks for watching this video. Uh, please come to my office hours tomorrow.
Thank you. Like and subscribe down below.